Hi, welcome to Quantum Field Theory Lecture 11. In the last lecture, we have seen a useful but tedious way to evaluate quantum field theory amplitudes. It is called the Wick theorem. And today we're going to see something much cooler, something very useful, a technique based on so-called Feynman diagrams, introduced by Richard Feynman, and really intuitive to use in order to evaluate QFT processes. So overall, what do we want to know? We are interested in what happens to an initial state when it turns into a final state, and we want to find probabilities for that. We have found an S matrix, a scattering matrix, that represents this transition process, but we're interested in a change. So we subtract 1. So this combination S minus 1 represents actually the overlap of initial and final states, or the transition from an initial final state, where really the initial and final states are different from each other. This is what we want to study. Now, let us just formulate the rules first, and then we'll see how they're actually connected to the stepwise evaluation by the Wick theorem later. Now, the rules are: draw external lines for each particle in the initial state and each particle in the final state. Assign momenta to each line, and for charged particles, add an arrow to the line to denote the charge flow direction. So, for example, for an incoming particle psi, here's the vertex where it connects to, so it comes in. It's incoming, so we have an arrow in this direction. The charge flows in the diagram. If it's outgoing, we have a vertex where it leaves, and the arrow is directed from the vertex, so it goes away. The charge flows out of the diagram. For the antiparticle, denoted typically with a bar or star or dagger, we have the arrow out of the diagram, so the charge seems basically to flow out of the diagram. The same as for an outgoing antiparticle, the charge flows in. This is the convention, so it doesn't really matter what you call particle and antiparticle, but it makes sure your Feynman diagrams conserve the charges. Let us consider the simplest example. We just have a theory where in the Lagrangian we have interactions of the type 5 psi bar psi. So we can draw following diagrams. We have charged fields where the outgoing antiparticle is denoted like this. Look, already here, this is actually backwards. We actually swap this. So this is an outgoing antiparticle, this is an outgoing particle. So now we have the charge flow arrows go through like this, so they create a connected graph, and that denotes the charge is conserved. So you could see this for a process, for example, as an uncharged scalar field phi that doesn't carry any charge, decays into two charged scalar fields, and one carries charge. For example, this could be something like an E minus, like an electron, and then the other would have to be an E plus particle in order for the total sum of the charges, to be equal to zero, because the initial decaying particle has charge equal to zero. So this is essentially a bookkeeping procedure that ensures the charge is conserved by the Feynman diagrams that you draw. So for each diagram, there is a term in the expansion of this amplitude, and we can now use this example of a scalar Yukawa theory that I mentioned before, that we also have introduced in the previous lectures, where the only interaction term is just some interaction constant y times phi times psi bar times psi, where phi is the real scalar field and psi bar and psi are the components of the complex scalar field. So the rules are now that we have to, after we draw the external lines, we also connect them by vertices and add momentum labels k to each internal line. And for each vertex, we write a factor negative iy, where this is the coupling constant, times 2 pi to the 4 times a four-dimensional delta function that conserves the form momentum flow in this vertex. So the k is a sum. This runs over all the momenta flowing into the vertex. We'll see in a little bit what it means. So for each internal line, then, so this is the rule for the vertex. For each internal line, then we write a factor that is an integral over those momenta k, and is essentially the propagator. The propagator in the momentum space, I divided by k squared minus m squared, where m is the mass of the propagating particle, and this I epsilon prescription means that it's the Feynman propagator. However, for practical use, we can drop it and just imagine that we would have written it usually. In our theory, we only have m phi and m psi, so there are just two fields that can propagate, for example, for now. Now let's go back to the phi decay. So the abstract notation would be phi going to psi psi bar. This is the decay process. On the diagram level, we would have to draw like incoming particle momentum p goes in this direction, and then we have two outgoing particles that have momenta, let's call them q1 and momenta q2. They are outgoing momenta. However, the charge flow is like this. So the antiparticle has the charge arrow going in this direction, and the particle, the charge arrow going in this direction. So it indicates the charge is conserved by the diagram. Now we apply the rules. So for this object, the matrix element of final and initial state s minus 1, we get the negative iy, 2 pi to the 4, and the delta function that conserves momenta that flow into the vertex. What does it mean? So p flows into the vertex, so it comes with a positive sign, and the outgoing particles q1 and q2, they're going out of the vertex, so we add them with a negative sign, so we have minus q1, q2, and then we're done. This is actually the same result that we got from direct computation using the creation and annihilation operators and the decomposition of fields. And so with this diagram and the Feynman rule, we immediately get just the coupling constant times the momentum conserving the delta function. That was quite neat. And this is the lowest order diagram for this process. This of order y in the coupling. So there could be also higher order diagrams, but we will discuss them later. Now let us just consider another process, phi real scalar mediated scattering. That is the lowest order process of order y squared. Why is it y squared? Because it has two interaction vertices here, and we have two psi particles coming in and exchanging a phi particle, and again going out. So the momentum flow goes like this, and also the charge flow goes like this. So there's a particle coming in, there's a particle going out, arrows go through. Same here on the other side. We exchange the phi, the momentum vector here goes in this direction, we call it k, and the others, the incoming, we call p momenta, and the outgoing we call q. But that's not the only diagram we can draw. We can also draw another diagram, because we don't really know from which vertex the particle with momentum q1 came, so we have also to attach it to the other vertex, which means basically flipping the diagram in this in this axis here, so it gets a twist. Just for future reference, this diagram or this interaction is called the T-channel interaction, and this one is called U-channel interaction. Our names are kind of arbitrary, but it's convention to call them this way. I will discuss later what they relate to in terms of kinematics. So using the Feynman rules now, we can write down the amplitude based on these Feynman diagrams up here. So this essentially equal, represents, first of all, we have two vertices and negative iy squared, and then we have the integral over the k momentum with the propagator, I divided by k squared m squared, and each vertex has added also this two delta functions with the 2 pi to the 4 factor, so we get a total 2 pi to the 4, 2 pi to the 8, where we have one delta function here conserving momentum as P1 is coming in and Q1 and K are going out. So we have these factors here. And the other vertex, we have K going in plus K, P2 going in plus P2, Q2 going out minus Q2. Same sums of the momenta give you the delta functions here. After we perform one of these integrals, setting K equal to, for example, P1 minus Q1 in this diagram, and we can just do it and insert it right here. And then here we set K equals to P1 equals to Q2, P1 minus Q2. We also set it equal to P1 minus Q2 and insert into this diagram. We saw in this delta function, we see that we get the same delta functions that just conserves the total momentum. P1 plus P2 minus Q1 minus Q2 is just the total for momentum conservation of the diagram. And the corresponding case here turned into P1 minus Q1 squared and P1 minus Q2 squared. So we have a D-channel propagator and the U-channel propagator up here. The prefactor, the I from the propagators I have pulled out, and we have the 2 pi to the 4 times the total momentum conserving, the momentum conserving delta function. Simple amplitude for this psi scattering process. Well, just a couple notes are in order. The diagrams are added because we have exchanged in the final states, we swapped the two particles here, basically, and they are bosons, so we add the diagrams. If they were fermions, which we'll have later in the course, we would have a minus sign between the diagrams. The propagators, show the exchange of a phi particle that is off shell. It means that the k squared doesn't have to be equal to the m squared for those particles. They are not real particles, they're virtual, they are not really satisfying the so-called dispersion relation that their total form momentum squared is equal to the mass squared. The last delta function ensures total energy momentum conservation and is always there. We will refine our rules slightly in a little bit, but just an observation, the total form momentum always has to be conserved. Then there are also higher order diagrams that we will discuss at some point later, but just an example, a y to the 4 diagram with 4 vertices can be constructed this way. So we have 2 vertices as before, but now we have 2 other vertices where we have a loop of psi's inserted. There's even higher order diagrams where we have 6 vertices, where we have in the loop of psi's, we also include another propagator of phi, so we have essentially 2 loop diagram and 6th order in the coupling y. Those have certain difficulties in terms of divergences of the integrals, but we will cover this in future lectures. Now, let's have an explicit example how to connect this to the Wick theorem. So let's say the amplitude for psi to psi scattering can be written down explicitly at second order in the expansion of the S matrix in the exponential description. We expanded. The first term is 1, so it got just cancelled by this minus 1. Then the second term is this I integral over d4x over the 1 interaction Lagrangian. The next term is the double integral of time ordered product of Li at x and Li at y. And we sandwich it in between these two states that contain 2 psi particles with momenta p1, p2, and the final state q2, q2, also just psi particles. Well, to evaluate this, we insert the definitions of L, so we get a y squared here. There is we actually get a y squared on 2, because here is a factor 1 on 2, and from the expansion, because here, remember, there's the 1 on n factorial in the expansion of the e function, of the exponential function. But this 2 will be cancelled later by a symmetry factor. Never mind, we have this diagram. We insert just the definitions of the interaction Lagrangian, phi multiplying psi bar psi, and we have the 2 integrals here. So another side note that we need to evaluate it is we can do an interesting game also with the psi fields. We can decompose it in its positive frequency mode, negative frequency mode, where here we have annihilation operators and here we have creation operators. Here I've written them down for you again. Here, for example, psi dagger, psi dagger. Now, yes, psi plus has this annihilation operator, which we call B, because we call the annihilators of the particles we call B, and the annihilators of the antiparticles we call C, right? So A and A dagger are the creators and annihilators of the quanta of phi, and the B and C are the creation, and B and C dagger are creation and annihilation operators from the field modes of psi and psi bar, because they have twice as many modes. They always have a particle and antiparticle mode. So what we can do now is to take this psi plus, for example, and apply it to the initial state, right? Here we see what happens if we put it next to the initial state, where in the initial state we have two psi particles that have been created from the vacuum by this creation operator B with a momentum P1 and P2. And there's the relativistic normalization factor square root of 2EP1 and square root of 2EP2. Then we have, this is essentially the initial state here. Then we act on it with this psi plus. Just put it in, and then we see what we have to do is to evaluate the diagram. We can commute this B operator with a, for example, B dagger operator. And when we actually have commuted it through, one pair of creation and annihilation operators disappears and we get the commutator for it. You can just try working out yourself. It's a simple calculation. You get this B dagger here. P2 survives, but B dagger P1 is gone because of the commutation with this B here. And we get the delta function that allows us to evaluate the integral of in this field decomposition of psi plus, and sets this k equal to P1. So we have this exponential e to the negative I P1y, and this is just the state which the initial state which would only have which only contains the particle momentum P2. So a notation, we can shorthand this as psi contracted with the initial state that contains these two particles P1, P2. When I contract with a P1 particle, I just get an e to the minus I P1y from this psi y, and the initial state with only particle P2. So particle 1 is gone by the contraction. Okay, this is good. So this allows us essentially to evaluate the amplitude by use of these external contractions and the internal constructions by the Wick theorem that we learned last time in lecture 10. So what are the possible contractions we can have? We can contract those particles here. Okay, so those particles psi, the part that are contain particle fields, we can contract with the particle states out here. For example, with P1, and this one we can contract with P2, well, yeah, vice versa. This one we contract with P2, and this one we contract with P1. And those fields here, the psi bar fields, they can be contracted with the particles in the final state that are coming in as a bra vector. So here they are, in terms of the operators, they are compatible with dagger fields, right? Because they are Hermitian conjugated. So we contract the bar field to the other side, like this. So we contract this with Q1, and this one we contract with Q2. And there are two possibilities to contract. Of course, we could contract this one with Q2 and this one with Q1. Right. So, and this freedom to swap them corresponds actually exactly, just at this point I want to mention, that of swapping the final states Q1 and Q2 and getting a T-channel or a U-channel topology in terms of diagrams. But in terms of the contraction, it just gives us, it's just the freedom of contracting them with different fields. And the phi x, phi y is just the usual Wick contraction that gives us the propagator of the phi fields. Now, there's the possibility to swap x and y, because this amplitudes are x, y symmetric, so we have the same expressions where x and y are interchanged, but they're actually the same. And so that cancels this 1/2 factor in terms of in this expansion. So this 1/2 factor is gone. Usually also this n factorial factor is canceled just by the number of contractions you will do, so it always disappears in this expansion. Now what we have is the exponential functions from the initial and final state contractions, and the Feynman propagator from the Wick contraction, right? So the Wick contraction gave us actually the Feynman propagator, which is the proper momentum space representations with this exponential function and the integral over k, and then we have also the integrals over the spatial coordinates x and y. So now grouping the terms, we can get a total e to the negative I k minus q1 plus p1 times x, and another e to the negative I p2 plus minus q2 minus k. Integrating over x and integrating over y here actually gives us delta functions. This and this become delta functions here and here, but and the propagator for now remains the same. So we just want to construct delta functions from these integrals. This is the definition of the delta function. And then we have two combinations of those from the two possible contractions of the external lines. We get this combination of delta functions and this combination of delta functions, and I said that corresponds to the T channel and the U channel, actually, just the momentum combinations. And now we can evaluate the last integral and get rid of one of the delta functions. So we get the two propagators here. The prefactor is I from the propagator is negative iy squared. And we get this total momentum conserving delta functions at the end, combining all the delta function integrals. Well, this matches exactly the diagram on page 6 that we had here. Well, it's actually page 3, never mind. So this matches exactly this diagram and the amplitude that we constructed from it. And let's call page 6 page 6 because it shouldn't page 3 because it is page 3. Right. Now, there are other less interesting contractions where we can contract the external fields with themselves here and internal fields also with themselves. Yeah. What does it correspond to in diagrams? It's actually that the external fields just are free propagating particles, and those are like three propagator contraction of the fields themselves, and it gives us a so-called vacuum bubble, a vacuum amplitude, which renormalizes the vacuum energy, but we have set the vacuum energy to 0, and all other quantum corrections to it are also set to 0 by the appropriate introduction of an arbitrary constant. So this is not an interesting diagram, really. Now we can refine our Feynman rules, and first let's define a transition matrix element, right? So this evaluation of the S minus scattering matrix minus 1 between final and initial states always leads to a form where you have an I up front, we have the so-called transition matrix element A final initial or T final initial. Sometimes people write also T final initial for that, with a 2 pi to the 4 and the total momentum conserving delta function. So now we can define the Feynman rules to obtain I AFI. So this is what we really call the amplitude, the interesting quantity. The rules are draw all possible diagrams with appropriate external legs and ensure the form momentum conservation at each vertex, right? So before we saw that if we use the rules, the delta functions will conserve the momenta, but we can also just conserve the momenta by hand by just writing the appropriate sums in there. Then we write for each vertex, we write a factor negative IY for the amplitude. We write a propagator for each internal line without the integral, just the momentum space representation, I divided by k squared minus m squared, where m is the mass of the propagating particles. And now we also integrate over all free momenta, k flowing through closed loops with an appropriate d4k over 2 pi to the 4 integral. We will discuss loops in a second, but just want to mention that loop momenta are not fixed by external momentum conservations, and so we have to sum over all momenta by doing the integral. So now, applying the rules again, this I A psi psi, the amplitude is just negative IY squared, and then these two propagators, sum of the two propagators of the T and U channel. Perfect, that matches exactly what we were finding by this technique and by the previous evaluation above. So now what I want to mention is that the physical process that we are interested in are depending on the absolute value squared. So this A dagger A products of these amplitudes, and we will come in the next lecture to the evaluations of those products. There are important caveats we want to mention. So we define the in and out states as eigenstates of the theory. However, strictly speaking, QFT, no particle is really free, and there are always virtual particles flying around them. So there's some caveats we have to consider when we construct diagrams. So one caveat is that we only consider connected diagrams. This kind of disconnected bubbles are always disregarded. They will not affect our physical processes, and that loops on external lines, this is really connected to the definitions of the free in out states. The loops on the external lines are also not considered in diagrams. This is essentially called, when you cut off these kind of loops on external lines, it's called amputation of the loops, and this is an ugly name, but this is called an amputated diagram. So you are not considering any loops here, but you could consider loops on internal lines. And this kind of derivation or this kind of statement can be made precise, and in an advanced QFT course one can go through all the derivations, or it's a nice discussion in Steven Weinberg's book on this topic. And overall, this kind of procedure is called the LSZ reduction formula, that shows that indeed only those diagrams with amputated external loops and no separated back home kind of bubbles contribute to our amplitudes. These are the rules and to construct diagrams and write down amplitudes based on the Feynman diagram technique. And in the next lecture, we will see how they're used to actually extract physical observables out of them.